Okay, let's work on question 3. So here the first part is pretty standardized. State Stirling's approximation formula conclude that n factorial is theta of this thing. So we know that the Stirling's formula is n factorial is approximately square root 2 pi n of n over e to the n power. So we kind of just drop the constant factor and we get this. So that's pretty straightforward. For part two, find the asymptotics of 4n in theta notation, and more precisely, find suitable constants for a, b such that f of n is equal to that, and it holds that this is this. Okay, so I kind of just work my way around this. I know that I have to start with this, right? I have 4n choose n. And then this is just using the definition of choose. I have this. And then I approximated each one by the Stirling's formula, so I get this. And I just cross out constant things over here. And I just realized that, okay, um, great, I have this over here, right? And the next what I do is I just simplify it, I just cancel out the coefficient, and yeah, I get this. So then what my A and B are is I just get this thing and I just extract the coefficient. This is just simple algebra bashing. Once you know you need to write it out this using Stirling's formula, it's this calculation. There's not much to say about that. For part B, we want for integer n greater than 1, d and be the positive divisors. Let this be this. Um, show that this is a Euclid's totient function. Show that g of n is this is multiplicative. You can use this and state it clearly. So essentially what I want to do is I want to show this thing, the function g is multiplicative. So what it means by multiplicative is that if f of mn is equal to fm times f of n, when GCD of m of n is equal to 1. So what I do is I know that I just set m and n be integers such that the GCD of m n is equal to 1. I know that every divisor k equals a times b, where a is part of m, b is divisible by n. So then my g of m of n is just going to be the sum of everything from inside m and sum of everything inside n of this thing over here. Because, yeah, that's kind of just how I set it up. Let me move this over. So then what I do is I know that these two functions by definition are kind of multiplicative. That's the property we know. So then we know that this thing AB is equal to this is equal to that, so I can just split it apart. So then my G of Mn is equal to the sigma of like A is part of M, B is part of N. So then we would have this, right? It would be split apart. So then we can just put the sigma because the A parts are and M parts are independent from B and N. We can just extract it out from the sigma loop. And now we can see that this is just G of M, this is G of N. So G is multiplicative. So the major thing in this question that should be taken away. Oh shoot, I forgot to open my camera. But the major thing that should be taken away is that like I do want the M and N to be like 1. And I just kind of set it up so that everything in A is everything from M and B is everything from N. Because I know that GCD of M and N are equal to 1, so then A and B have nothing, in common. That's kind of the idea. And then I just kind of put the sigma so that I just kind of get what I need, and I just extract out the independent parts and then regroup it so that I get my G, M, N, and G of N. Okay, part C. Let T1 equals B E1 and T2 equals that. B2 for us on the same vertex set. Let G of VE be the union of T1 and T2. Explain why G has at most this many edges. Okay, so the idea behind this is that we have two trees, and it's a forest on the same vertex set. So yeah, we have this. These are our conditions. We know that the total of this should be less than or equal to, when we combine it, is less than or equal to the edges of 1 plus the edges of 2. And each forest by definition, because if we have a forest, there should be no loops and everything is at most connected to like this. So that means that mm, each tree, when we add something to the thing, it would just only have maximum of one more added to something else. Because if I have anything added to anything other thing, I would have a cycle which would not work out. So the maximum a tree can have is v minus 1 edges. So now I add up the both of the trees, which is v minus 1, v minus 1. So at most I can have 2v minus 2. So then I just extract out the 2 factor, and I know that my edges has to be less than that. So that I showed that successfully. For part 2, conclude that G has a vertex of degree less than or equal to 3. G has a vertex of degree less than or equal to 3. So, yeah, I don't know why it's not. Okay, so I'll explain it. So I know that the sum of the degrees has to be 2 times the number of edges, right? Because like the way the graph is set up. So I suppose that all of the vertexes have degree greater than or equal to 4. So that I would have 4 times v. But unfortunately, 2 times e of this thing is only to that. So then that means that there must have been a vertex with degree less than or equal to 3. I think the idea is that like this is just a proof by contradiction. I should have laid it out more clearly, but the idea is that like I just assume everything's connected to more than 4 things, but then because we want to show that it's less than or equal to 3. So then if everything has 4, but then if you have 4 times of that, then you try to match to what we have. So then the number of edges would have been at most that amount. So then we put that in and we're still less than that. So then it have like we still have to put one more vertex in. So that's the idea behind that. And then for part 3, using induction or otherwise show that G has a proper 4 coloring. Proper 4 coloring, okay. So we kind of, what we can do for this is we can just use induction on the number of edges. So we assume that there was this n is just that number of edges, vertices. If n in our base case is equal to 1, we have 1 vertex, 0 edges, so we can just color it one thing. Awesome. For our inductive step, our induction hypothesis is that assume all graphs formed by the union of two forests with k vertices are four colorable. So then we let our G be the graph with all k plus 1 vertices by so then by 2 we know that G must have vertices have a vertex with degree smaller than or equal to 3. So then we remove that vertex. So by the induction hypothesis, the G of that thing is 4 colorable. But when we add feedback, since we have at most 3 neighbors, then it could be the remaining color. So it's 4 colorable. So then the induction is complete. So that's how we prove this. So basically the idea is that we have just a lot of graphs. We know that there must exist a point where it's only connected to at most 3 things. So if the 3 colors were different, I still have a 4th option. So that's why it's valid when I add it back. And it's just induction. It's just classic induction. And for part 4 is G a planar graph? Justify your answer. Using Kurowski's theorem, basically we just want to check if there's K5 or K33. So inside here, unfortunately, it is possible to have K33, so it's not planar. Because we could have technically like these kind of things where it's possible. So yeah, that's why K33 is possible and it's just not doable, in other words. Okay, so that's it for this question.